Okay, so the result in the end is that the semi-classical limit of LQG dynamics, and more precisely, it is in the reduced phase-space formulation, because over there the dynamics is very clearly defined, because there is a Hamiltonian reduced phase-space formulation. Okay, is correct. Namely, it reproduces classical general relativity. Reproduce. Is classical. And that's the classical Einstein gravity. Classical Einstein gravity. Okay. And this is some result. It is actually some result very new. You can see, because this is one of the recent work by myself and my collaborator Hong Gong Liu in this paper. Okay, and over there you can find details how to go from the semi-classical limit of operator and to the semi-classical limit of dynamics. Yeah, and how to reproduce classical gravity from full loop quantum gravity dynamics. All right, so I think that's all for the semi-classical limit, and so now I'm going to switch the topic and talk about entropy, talk about quantum statistics in loop quantum gravity, and relate to black hole entropy. This will be completely different, very much different topic. Okay. Now let's talk about quantum statistics. Statistics of a loop quantum gravity surface. So in this topic, this is well, this is not this is the sub area. So black hole entropy and quantum loop quantum gravity black holes. It is a sub area in loop quantum gravity, which is, however, not completely relates to the well, it relates to the main line of development of loop quantum gravity, but it is also there is also an open issue about how exactly relates to loop quantum gravity black holes to the full theory of loop quantum gravity. So all this lecture we are talking about is a full theory of loop quantum gravity, including the quantization and Hamiltonian constraint, Hamiltonian semi-classical analysis, and so on. But there are several sub areas in loop quantum gravity which are sort of doing so-called reduced simplified models, or reduced models. So including, for example, loop quantum cosmology and also loop quantum black holes. And people consider just simplified models without really considering the full-fledged Hamiltonian or Hamiltonian constraint in loop quantum gravity, but just considering some very simple situation of the theory, and try to find out some results. And here, studying this quantum statistics or relates to black hole entropy is also along that line. So you can see that in this calculation, you don't really talk about Hamiltonian constraint and so on. You just look at some very basic kinematical feature of loop quantum gravity, or geometrical feature of loop quantum gravity. Okay, so in some sense it is much simpler. Okay, so now let's look at a surface in loop quantum gravity. Let's look at a general two-dimensional surface. This is just a two surface. Okay, so what we are going to do is to do some statistical mechanics inspired by loop quantum gravity on the surface. Yeah, and the observation is that in loop quantum gravity, let's consider these two surfaces is a macroscopic surface with total area. So this total area we call it A. Yeah, and for total macroscopic area. Okay, with total macroscopic area A. So and this A is of course it's much larger than Planck scale. So it is like a few meters or it's very large. It can be larger than meters and even larger. Okay, and however, we know that in loop quantum gravity, these macroscopic area are made by small areas, namely. Okay, so you can view this surface is embedded in a very fine lattice, and also this surface is partitioned by small surfaces, small phases. Okay, okay. And each of the phase we have flux and we have area operators and so on. Yeah? And each of the phase or each of the small surface. So this is the small plaquette, or no, this is not really our plaquette. So this is just you can view you have a very fine lattice, well, and there are a lot of spin network edges cross the surface, and each edge has a J, has a quanta of area, and then these plaquette, this small square, and I will call it the facet. It just means small face. Yeah, I just call it facet. It means it's just a small face, making partition of these two surfaces. And this facet has a microscopic area. Yeah, has a microscopic area J. Yeah, J. Okay. And over here it has J1, J2, J3, and so on. Okay, so you have microscopic area, and it's microscopic area labeled by J. Okay, this facet has microscopic area, and the area is just given by the area spectrum 8 pi g Newton h bar gamma square root ji plus 1. So I labels the facet. Yeah, so this is the certain i's facet. Okay, it carries a microscopic area, and you know the relation between the macroscopic area and the microscopic area. So the macroscopic area is just the sum over I and of those microscopic areas. Okay, so here is the punchline. Sorry, so the Babel image parameter is beta. So here we always use beta for the Babel image parameter. Right, and so you view this surface is just it's a surface. You have a lattice. You have a lattice of the space, and you draw a surface, and then these lattice edges make punctures on the surface. Yeah. Okay, so in our previous setup, so consider this is a cubic lattice. Okay, so this is our cubic lattice gamma, and then this surface. I mean, I suppress one dimension, and this surface just goes like this. Like this is this surface. and this little facet is just things like this, things like this. Right? And then each facet carries a spin j, because each edge here carries a spin j. Okay, so then the total area is just a sum over all the small area, all the microscopic areas. And here, because we are going to carry out the statistics, and also because we assume that all the microscopic areas are of Planck scale, and we consider a macroscopic area, namely you have almost infinite many small facets. So this is the surface which is macroscopically smooth. It looks like a smooth surface. It means that you ignore the size, and the size of those small faces, those facets, they are very, very small. And so you have almost infinite number of facets. So here you assume the number of facets. There is something like a thermodynamic limit that goes to infinity. Okay, so this is the assumption of our calculation of our model. All right, so now we can consider these facets, all those facets as a statistical ensemble. Okay, and we can make analog between two surfaces. So on one side it is a two surface in loop on gravity, and we can make analog with statistics. And we can compare with, for example, a gas in a box. Okay. And so to compare, so both of them are ensembles. So uniform gravity is an ensemble of those facets. Yeah. And in the gas in the box, in ordinary statistics, they are ensembles of identical particles making the gas. Okay, and both we have a macroscopic state. So when we consider quantum statistics, firstly we need to distinguish what is macroscopic state, macro state, and micro state. Macro state and micro state. Okay, so for two surfaces in loop on gravity, the macro state is that the area. You have the total area. Macroscopically, what you observe is this area. So this is a macroscopic state. And for gas in the box, it is you have total energy. So total energy. So it is a conserved quantity, and it is something you observe macroscopically. And you also have, for example, total number of particles. Okay, or you can also say you also have total volumes and so on. Right, and but here for loop on gravity, so we don't consider so the total area is conserved, but we don't consider the total number of facets is conserved. Here we don't fix. We don't fix. Okay. So a consequence is that we don't have things like chemical potential. Yeah, you can include chemical potential if you fix the total number of facets. You can include chemical potential. There are indeed people doing this, but at least for our calculation, for this discussion, we don't consider chemical potential. Okay, so now what is the microstates? The microstates are just all these facets, each of which carries a spin, carries a quantum number, J. all the facets. Right. And the microstates for the gas is that you have all identical particles, and each of which carries energy, Ei. So this is particle energy. The particle energy. Okay. And moreover, you can, so for the gas in the box, you know the total energy is sum over all the particle energies. And here, the for loop quantum gravity, you know that the total area is the sum over those areas of the facet. Okay. All right. So now you can see there are really some analog between surface in quantum gravity and gas in the box. Okay. So now what we have is an ensemble of identical facets carrying quantum number J. Okay, and you can also understand those the microstate of identical facets using our the standard language of statistical mechanics. You can just describe this ensemble or understand this ensemble by distribution of J. Distribution of J. Okay. So what is distribution of J is Nj. It means that where Nj is the number of facets carrying the same spin J. Is number of facets carrying the same J. So here we don't consider J equals to 0. So we always consider positive J, because J equals to 0, it has no contribution to the area. Okay, so we only consider positive J. And so here we consider a distribution of J. And remember, if you just recall your statistical mechanics, and when you for example, deriving canonical ensembles, and this is exactly what you do. You just consider identical particles and a distribution of energy. Yeah. And given the energy level, how many particles is at these energy level. Okay, and now once we have a distribution of J, we can count the number of microstates with the given distribution. So now let's say given a distribution, arbitrary distribution Nj, and we can count the total number of microstates, and all this, and because of the principle of statistics, all those microstates are equally weighted. Okay, and we just count them. So this is the total number. I call it D. Okay, so this equals to, well, again, just the same. Just make the analog with gas in the box, and in your statistical mechanics computation, you should all know the result. This is just given by firstly total total number. So this is the total number of facets or particles, factorial, and product all energy levels. Yeah, here is all j's and factorial. So nj factorial, and each energy level has certain degeneracy because here you have spin as your quantum number, labeling the energy, analog of energy level. But given the spin, you have a degeneracy because you have various magnetic quantum number. So your degeneracy is 2j plus 1. So given a representation space j, you have degeneracy 2j plus 1. So you have to include the degeneracy. All right. So this is the total number of microstates in counting by using standard statistical mechanics. So now again, the same procedure as in statistical mechanics. We ask the question that what is the most probable distribution? What is the most? So this is the microstate for arbitrary distribution, and we ask the question what is the most probable distribution? The most probable distribution is the maximum of this number. It's the maximum of total number of microstates, because by the principle of statistical mechanics, every microstate are equally weighted, and so the most probable distribution is the distribution which occupies maximum number of microstates. Now we just need to compute what is the most probable distribution. What's the most probable distribution? Namely, the maximum of this number of states. Okay. So how to get maximum? You just compute the variational. You just use variational principle. Variating your distribution. Okay. Well, but this variation has should subject to a constraint, because you have a fixed total area. So this is a variation. It is not a free variation. You have to have a constraint. Just like in statistical mechanics, you have a constraint because you fix the total area, fix the total energy. The total energy is conserved, so you have to subject to a constraint for the total energy. So here is the total area. So this constraint, I still use C for this constraint, and it is a function of distribution equals to area minus sum over J in J. Okay, so it just means the total area, and this constraint has to be 0. Okay, so this is in the bracket. It's just the area corresponding to a J, and then in front of the bracket you have the number of facets having the same J. Yeah, so that's why you multiply Nj and then you sum it over all J. Yeah, then you get total area. Yeah, and this total area has to be conserved, has to be fixed by this A. All right. So now you just compute the variation. Okay, and you just variate. I mean, to plug in a constraint, you have to insert a Lagrangian multiplier. So we do the variation with respect to logarithmic of t. Okay. Minus t inverse. So this t inverse will be the Lagrangian multiplier. Well, in statistical mechanics, we know that this Lagrangian multiplier will be temperature. So that's why I just put T inverse. Conventionally, I divide by 8 pi G HR theta. So the Lagrange multiplier is T inverse divided by 8 pi G HR theta. And the variation should be 0, and then you reach the maximum of the distribution of the number of states. Right, and this is Lagrange multiplier. Okay. So the only difference from the standard statistical mechanics is that we don't fix the total number of particles. So here you only have a single constraint, which is the total area. Okay, and then well, all this calculation is just the same as statistical mechanics. You do this variation, use the Stirling's approximation. And also from statistical mechanics, you know the result. The result, the most probable distribution is just a Boltzmann distribution. Okay? And you know the solution. You just solve this variation equation, and you know the solution, which is just Boltzmann distribution. Solution, and I'll call it n bar J. Is just the Boltzmann distribution. Okay, and namely n bar J, and then divided by the probability distribution. So n bar J divided by total number of facets equals to 2J plus 1 e to the minus T inverse 2 plus 1. So it's like this, the area spectrum J plus 1 square root is something like energy, and this Lagrange multiplier plays a role like the inverse temperature. Yeah, and here you get a degeneracy 2J plus 1. So you see the formula just, the result is just a Boltzmann distribution. Okay, and from this expression, you immediately can have a consequence. Is that suppose you taking this formula and summing over J. Okay, summing over J, it means that you sum over J. Well, here it is J from 1 to infinity, and also J is half integer, and 2J plus 1 e to the minus T inverse J plus 1, and this equals to sum over J and J bar divided by sum over J and J bar. Okay, and equals to 1. Okay, so this is consequence of the above formula. Okay, right, and now you get this equation. And you can use this equation to solve T, right? And this equation, left hand side you sum over J, and this is just a function of T, and right hand side equals 1. So you can use this equation to solve T, and the result, the solution is, let's say the solution is T0 minus T0 inverse divided by 2 pi. So later on you will see why I want to have divided by 2 pi, and this equals to 0.274, and so on. So it's like in this case, you can solve the temperature. The distribution uniquely fix the temperature. Well, in ordinary statistics, you are not really fixing the temperature because you have another conservation law. You have another constraint, which is total number of particles is fixed. Well, here we don't fix the total number of particles. All right, so now you solve the temperature T, yeah, and you also get the solution. You get the most probable distribution. All right, and now what you need to do is plug in back to the number of state. You just count the number of state uh, in probable distribution, in most probable distributions. You plug in the solution. Okay, and what it is, so let me just proceed the computation. Okay, so these give you firstly logarithmic n bar j and minus sum over j log n bar n j factorial. So this is log of this total number factorial plus sum j n bar j log 2j plus 1. Okay, so this guy I'm just make a shorthand notation. So this guy I just call total number capital N, capital script N. All right, and now I'm just using Stirling's approximation for the first two logs. So I get log N, N log N minus N. This is for first log minus sum over j bar j log. Again, Stirling's approximation. Okay, and plus the last term. Okay, right. So firstly, well, you find well, the last term you can ignore this last term because this term will just cancel with this term because the summing over j of n bar j is just a capital N. So this term you can ignore, and well, let's look at this term. All right, and look at this term. This is just a minus. Well, you just plug in the expression for n bar. J plus 1 minus 1. Okay, and then log of this guy, which you get log n plus log 2j plus 1 plus log of this exponential, which is this is just minus t index plus 1. Okay, and now you just look at again this term. Okay, so firstly, you get just n log n of this. The first term, you see, well, let me expand anyway. So you get, I'm just computing this expression. So firstly, you get sum over j, 2j plus 1, ej minus t inverse j plus 1. Okay, and then times n log n. Okay, but we know that this is just the first term, and we know this is just 1. Okay, so you can see the first term is just 1 times n log n, but in front there's n log n. So first term just cancel with that. Okay, and what's the second term? The second term is well, in front this is just the n bar j. Okay, the second term it is just a minus j n bar j log 2j plus 1. Okay, and this term is identical to the last term. Okay, it's identical to the last term, and this term is just cancelled with the last term. and this term also cancel. And the last term, it is plus. You have minus and you have minus. So the last term, it is just a sum over j 10 bar j t inverse j plus 1. Okay, so you see, and as I mentioned, and this term cancel with this term, and this term cancel with that term. Okay, and the result is this guy. And you can see that this t inverse is just constant. You pull out the sum, and the rest part is just the total area. So result, yes, you get a nice result. The result is just the T0 inverse total area divided by a pi T h bar gamma. Well, this total area is sum over j 10 bar j. Well, this is just coming from the constraint. Multiply the coefficient. Okay, and this is just coming from constraint. Yeah, so because we always need to subject to this constraint. All right, so now you see that the logarithmic of the number of microstate, it is this guy, and this is just the entropy, right? Because what is entropy? Entropy is just given the macrostate, the total number of microstate. Okay, so now we got entropy of this L2G surface as is just a logarithmic d for the most probable distribution. It is just T0 inverse pi G h bar gamma times A. Okay, so you see that the entropy satisfies the area law. So given a surface, if you perform the statistics on loop quantum gravity surface, and the entropy of this first surface satisfies the area law. Okay, so you can imagine it's very much similar to the black hole. I mean, this is something we would like to expect for black hole entropy. If you remember, when we talk about black holes, and we say because by Bekenstein's black hole thermodynamics, you can assign a entropy to black hole, and black hole entropy satisfies the area law proportional to the horizon area, and it is the horizon area divided by 4. So now you can make this formula more contact with the black hole entropy. So you can just write T S equals to T0 inverse divided by 2 pi divided by gamma, beta. Sorry, and we should use beta because lots of literature use gamma for the Weber image prime. Sometimes I use beta, sometimes I use beta. I use gamma. Okay, so now we always use beta for Weber image parameter, and this entropy equals to this, right? And 4 times